Good. How are you doing today?
Doing pretty good.
Good. So what's going on in algebra this week?
We're reviewing right now, and I did the review, but there's only one thing and I don't understand, and I actually don't have any examples of it because it wasn't on the review, but it's on the test. It's linear programming.
All right. You've actually started out with three very difficult subjects. One is word problems, and I noticed that your word problems were harder than other algebra students' word problems. And you had three equations and three unknowns. And then you had piecewise functions. And
We
then
actually did
program.
linear before we did piecewise.
Linear programming is probably the most difficult subject of all to get in Algebra 2.
My problem is just being able to find the constraints and the
Well,
profit.
I have some problems from Dylan, I think. Let me see if I can find them that are linear programming problems. This is from a while ago. Not sure this is it. No, I don't think this is it. No, this was piecewise.
Yeah. I think it might have been even before that because we did linear programming at
It was.
piecewise.
It was. Hold on. Let me see if I can find it. Because without a problem, you have nothing to even talk about. Yeah, here it is. Let's see, that's a linear programming problem. And this is a linear programming problem. All right. This is number 3. Let's take them in order. I have 2 of them. Here's the key with linear programming problems. Most important thing is to identify the objective function. Okay?
Right.
And that usually is the function that you're trying to either maximize or minimize. In other words, in this particular problem, the profit equation is the objective function. If you read this paragraph, go ahead and read it.
The Sheffield volleyball team holds a big...
Not out loud.
Okay.
Just
Sorry,
no, that's okay. I always recommend people don't read it out loud because if you're in a testing situation, you're never going to be doing it out loud. You're going to read it to yourself. Notice the last sentence. How many of each kind should the team bake in order to make the most money?
So it's a maximum equation.
Well, hold on a minute. Let me expand this. So the first step of this problem is the same as the first step of word problems. Define your variables. And in other words, your profit. Now let's define your variables. What's X and what's Y?
X is the number of chocolate chip cookies, and Y is the number of sugar cookies.
And it's important to put those labels on them. In other words, it's the number. It's not the price. Okay? It's not the price of chocolate chip. It's not the price of sugar cookies. It's the number. How many of each kind should the team bake in order to make money? And the profit equation, which I'll call P for profit, is the number of chocolate chip cookies times the price. So it's $1 times X plus $1.50 times Y. That gives you, and let's not call it profit. I don't like profit in this case. Let's just call it revenue. Your total revenue is going to be $1 for every dozen chocolate chip cookies plus $1 times $1.50 times every dozen sugar cookies. In fact, if I really wanted to be specific up here, it would be the number of dozen chocolate chip and the number of dozen sugar cookies. Okay? That's the most important thing about linear programming, your objective function. Okay? Now you have your constraint. Well, your constraints are your restrictions. In other words, they will bake up to 20 dozen chocolate chip cookies. So X is the number of dozen of chocolate chip cookies, so it's one of my constraints. You can only bake up to 20 dozen.
Less than or equal to 20.
Less than or equal to 20, okay?
What? Oh, okay.
Okay, because you can only bake up to 20 dozen chocolate chip and up to 40 dozen sugar cup cookies. So Y is less than or equal to 40 is another constraint. And also the number of sugar cookies is less than or equal to 4 times the number of chocolate chip cookies. How can I write that? And it's not correct on this paper. So the number of sugar cookies is less than or equal to 4 times the number of chocolate chip cookies.
Y is less than or equal to 4x.
There's your 3 constraints. Okay? Now, here's the name of the game with linear programming. And linear programming is pretty unique. This is the only thing that you're going to do this with for the whole year. Okay? And that is, you got to draw the constraints. How do I draw? And you draw the constraints first. Well, if this is the x-axis and this is the y-axis, what does x less than or equal to 20 mean graphically?
It means it's a vertical line going through 20x.
Going through 20.
And since it's less than, it will be shaded to the left.
Okay, good. I'm going to shade all the area to the left. How about y is less than or equal to 40? What's that look like?
The horizontal line through 40, y.
So now we got this area. But what's the third constraint? How do I graph y is less than or equal to 4x?
You just graph the line, y equals 4x, but the shaded area will be below the line.
Okay, so y equal 4x goes through the x-intercept or the y-intercept of 0, has a slope of 4, So I'd go up 4 and over 1. Which side of that do I have to shade?
The right side of it.
Correct. So now my area is that area there. Okay? So now I have an area defined. And that's usually where you can stop. In other words, once you've looked at all the constraints, it defines an area on this graph. Now you have to examine the revenue function for all of your 4 points. That point there, which is 1, I'm going to call it. This point there, which is 2. This point there, which is 3. And also that point there, which is 4. So there's 4 vertexes to that shape. Sometimes there can be 5, 6, 7, depends on how many constraints you have. Okay? Now what we have to do is evaluate the revenue function at all 4 points. Well, what's R of 0, 0, or this initial point? That equals
0.
Okay, let's go to the right, point 3, R sub 3, which is, what are the x and y coordinates on point 3?
20 and 0.
What's R of 20, 0?
20.
What's R sub 2, which, what are the coordinates on R sub 2?
R sub 2, it's going to be 2080.
2040.
2040. Yeah, 2040. Jesus, I'm tired.
Okay, and what is that equal to? You plug in 20 for x and 40.
Wouldn't it be 2080 because 1040 is 0.1?
No? What we're looking for is this point right here.
Yeah, okay.
Okay, the x-coordinate is 20, the y-coordinate is 40. And that point is a vertex of our area that we want to consider. In other words, we know that the maximum revenue lies at one of these 4 vertexes. That's the essence of linear programming, is that your maximum or minimum, depending on the type of question, lies at the vertex of the area that you've shaded. And there's 4 vertexes to that area. So what is R sub 2? What's the revenue when I make 20 chocolate chip cookies and 40 sugar cookies?
R equals 20 plus 60. So you'd have 80.
80. So far, that's the maximum. We got one more area to look at. That's R sub 1. What are the coordinates on R sub 1?
1040.
Yeah. And that's usually the toughest part of these problems, is figuring out the coordinates on all your vertices. In other words, it's not clear. We have to do a few things. We know that y is 40, and so we plug it into here to figure out what x must be. Well, if y is 40, x has to be 10. And what's that revenue?
70.
Now what you do is you pick the biggest number.
So R sub 2.
So what's the optimum number of cookies to make?
20 chocolate chip and 40 sugar cookies.
You got it. Let me go to the second one here. Solving these isn't as important as setting them up. And all of them kind of have the same kind of stuff. In other words, you start out defining the variables, you start it, and then you define your objective function, and then your constraints are what, define your shape. Your critical points are the vertices of that shape, and then you substitute the values of the critical points into the objective function to come up with your conclusion. So in this one, what are my variables? Always go to the last sentence. You don't even need to read the rest of it. Just immediately go to the last sentence. What's it say? How many of each kind should the store buy? Well, it probably means there's two kinds of things. Talking real trees and artificial trees. So what should X be?
X should be the number of real trees, Y the number of artificial trees.
And you could say to buy, but mainly that's probably good enough. The number of real trees to buy, Y is the number of artificial trees. Okay. Now, objective function. The store can buy, that's a constraint. The supplier can supply, that's a constraint. The store is short of cash and wants to invest in the minimum feasible amount in trees. So the cost of whatever trees they are going to buy is your objective function. It's the cost equation. What is it?
So it's going to be 80x plus 160y.
You got it. That's our objective function. That's the function we're going to try to minimize. In other words, because they're short of cash, they want to spend as little money as possible. So once we graph our linear programming, we're going to find the minimum point. Okay? And let's go through some of the constraints. Sentence number 3. The store can buy between 20 and 90 real trees and up to 100 artificial trees. How can I write that as a constraint? What is it? How can I write the store can buy between 20 and 90 real trees? Let's say about X.
X is greater than 20, less than 90.
Greater than or equal.
So,
okay. And that covers that. And up to 100 artificial trees. So how would I write that?
X is less than or equal to 100.
X.
Y is equal to less than or equal to 100. Sorry.
And finally, the supplier can supply between 40 and 120 trees total. Wow. How do I write that?
X plus Y is greater than or equal to 40 and less than or equal to 120.
Correct. And finally, a fourth constraint is the number of artificial trees ordered has to be more than or equal to 2/3 the number of real trees. So artificial trees is Y. Has to be equal to or greater than, more than or equal to. Now I need to change that. That's a greater than sign, or equal to what?
2/3 X.
Yep. All right, now we have all of our numbers that we need. So now let's start graphing this thing. And this is really an integral part of linear programming, is the graph. Okay? We're going to start with the constraints, not the cost function. The cost function is what we're going to evaluate at the vertexes of our constraint picture. So the first thing I can do is say, well, x is greater than or equal to 20 and less than or equal to 90. So it's between my two vertical lines, right?
Mm-hmm.
Next thing, y has got to be less than 100. Now we're in this area.
Isn't it less than 120?
No, y is less than 100.
Oh, yeah. Sorry, I thought you were talking about the...
It is 100, yeah.
Yeah, it's 100. It's 100.
And let's take the next easiest one. Y, in other words, we've done that. Oops, I mean to do that. X is greater than or equal to 20 and less than or equal to 90. We've taken care of that one. Taken care of that one. How do I take care of the bottom one, which is, what's going on with Windows 10 here? Y is greater than 2/3 x. How do you graph that?
You just graph 2/3 x and shade above the line.
Where do I start?
And start at the origin, since it has another line.
Okay. So 2/3 x means up to over 3. Oh, that's going to be a line, something like that. Okay. And y has to be greater than that. So now we're in this area. You with me?
Mm-hmm.
Okay. And finally, the toughest one to graph is this third one here. Because you kind of have to graph it in two parts. First of all, let's rewrite it as two different things. In other words, first of all, x plus y has to be greater than or equal to 40. How do I graph that? Remember, at this point, we're in this area.
I don't know.
Well, manipulate this equation, and instead of having it say x plus y is greater than 40, let's have it say y is greater than or equal to minus x plus 40.
Okay.
You know how to graph that?
Mm-hmm. So put your 40 on the y, because your 40 is your y-intercept for the line.
Okay, we can do it that way. I'm not real fond of that way, but there's 40 on the y. The only reason I don't like that way is because that's not in our area, right? But we're close to out of time here. So if I graph the y-intercept, 40, then I graph a slope of -1, get perhaps something like that. Now we're in this area, okay? And now finally, there's the x plus y is less than 120. So how do I graph x plus y is less than or equal to 120?
Move over the x.
Okay. What's the y-intercept going to be?
120.
What's the slope going to be?
Negative x.
-1.
Negative 1.
Not negative x, -1. Remember, it's always, so there's our area. Okay? So let's number our vertex. That's number 1. That's number 2. That's number 3. That's number 4. What we want is the vertex that produces the minimum cost. So we need to find the numbers on each of these vertexes. That's always the next problem. What's the vertex on number 1? How would I find that?
I don't know.
Well, remember what that is. That is y is greater than or equal to minus x plus 20. What's the x coordinate? On vertex number 1?
20.
Plug it in. What's y?
40.
Now, if you plug it in down here, if you plug in 20
0.
for x, y is 0. So x is 20, y is 0. So let me see if I can label that. 20, comma 0. It doesn't match my picture because my picture was estimated. Now, we take that x and y value, we plug it into our objective function, t. What do you get? What's the cost at that point?
$160.
Correct. So the cost at point number 1 is 160. Now, we're out of time, so I can't do each one of those, but we need the cost at point number 4, point number 3, and point number 2. You can kind of imagine how I need to figure out each of those, right? I need the x and y coordinates of point 4, point 3, and point 2. Once I have those, I plug them into the objective function, and I have the cost for each of those 4 points. And then I choose the lowest one, because the store is short of money and they want to spend the minimum amount. Okay? Cole, I'm sorry, I have a new student at 4 o'clock. I don't want to really be late for her, so I'm going to go. But that's the basic strategy for linear programming, and it's correct. It's tough. If you want to spend more time on it next Monday, we can.
All right.
Okay? All right. Talk to you later.
Talk to you later.